While cryptography is mainly concerned about the encryption and decryption of data, there are also other important tasks which cryptographic functions help us solve. The reason why we need these other applications is that encryption on its own only ensures data confidentiality. If you remember from the beginning of the course, confidentiality is only one of the three objectives we need to achieve. Data integrity is an equally important goal. Cryptography can also help us achieve that, and now we will look at a couple of methods which help achieve integrity. To get to a point where we can talk about how to ensure integrity, first we look at a concept called hashing or hash values. Sometimes this is also called a message digest or a hash digest. A hashing algorithm is a mathematical model which helps us compress a message into a smaller space. The objective of a hash value is then that two messages can be compared against each other by comparing their hash values. If two hash values match, then the messages also are identical. Well, that is the idea anyway. It's important to remember that hashing and encryption are not the same thing. In fact, a hash value of a message cannot be used to recover the original message. Hashes have many various use cases. For instance, hash tables are a data structure that is designed for quick archiving and retrieval of information. Often also databases use hash values to retrieve information quickly. We can also employ hash values as a checksum. They are used to verify message identity. For example, we can determine if our network communications are intact or if there has been some packet loss on the way. Sometimes the checksums are also used to recover some of that missing data. The application that we will talk about shortly is the use of hashes with digital signatures. These different use cases also provide different requirements for the hash function that is used. Usually we distinguish between cryptographic hashes and non-cryptographic hashes. That is, when it comes to message integrity, we would use a cryptographic hash, but if we are concerned about error recovery or quick retrieval of information, we might use a non-cryptographic hash. So how does hashing work then anyway? Let's consider a very simplified example. This of course is not a cryptographic hash, but it will demonstrate the idea. So let's take a record such as someone's name. Let's say that name is my name, which is going to be Timo. And let's codify our alphabet somehow. Let's use a fairly simple codification so that A becomes a 1, B becomes a 2, and so on. So by counting the position of the letters in the English alphabet, we would get T is the 20th letter in the alphabet, I is the 9th, and so on and so on. So as a result of this calculation, if we add up the sums or this value for each of the letters in my name, we should get a result of 57. And then we would say that this 57 is the resulting hash digest. Again, this is a very simplified example of how a hash might work, but you get the idea. Cryptographic hashes are slightly more complicated, but not impossible to understand. So a cryptographic hash is a one-way function which is hard or even impossible to reverse. Let's think for a second what this means in practice. So let's call our hash function h, and our hash function also, because it calculates a hash value for a message, m, so m is a parameter for our hash function h, and as a result we get a hash value which will denote with a lowercase h. So what our requirement for a one-way function that is hard to reverse means in practice is something along the following. We should not be able to construct a reverse function h-1 here, which if given the hash value as a parameter would return the original message back. So in math terms, the probability for such message and corresponding hash value pairs for which this kind of a reverse function would exist is smaller or equal to negligible. So it should be very, very improbable that there exists such a function h-1 that is able to figure out what the original message for a given hash value is. So all in all, a one-way cryptographic hash function is a function which is easy to compute one way, so it's easy to compute the hash value, but given the result, the hash digest, it's hard to find the original message or hard to find the original factors which produced this hash value. Imagine it's much like breaking a drinking glass. It's very easy to do, but gluing the individual glass pieces together is quite hard, especially if you intend on making the glass whole again. The other interesting requirement for this hash function is that the function should be collision-free. That is, there should not be the chance that multiple messages produce the same hash value. In general, we say that a cryptographic hash function has 4 requirements. First, it must be easy enough to compute the hash. Hashing should not be a time or resource-consuming operation. Second, it's hard to generate the original input message based on the hash. Third, it should be hard to change the original input message without changing the resulting hash as well. The fourth and final requirement is that it should be hard to find 2 different messages which produce the same output hash. Here is an example to illustrate how such a hashing function could look like in the real world. First, we should notice that given a different input, we indeed get a very different resulting hash digest, as is demonstrated in these first 2 boxes on the top. So given a different input, the resulting hash is also significantly different. In the remaining boxes here, you can see that the input message only differs a little bit. Yet the resulting hash values on the right are very, very different to each other. So the idea is that the slightest change in the input message will result in a drastically different hash value as an output. Hashes themselves have many use cases, but they are particularly useful when they're used to create MACs, or message authentication codes. A MAC is a hash function that is produced using an individual key for each message. So a message authentication code algorithm produces unique hashes for each message key pair. That is, the hash is different for the same message if the key is also different. The hash can also be different for the same message and the same key. Also, time can be an input if we are really concerned about the integrity of the messages, but this is a side note at this point. Also, it's good to notice that a cryptographic hash is not the only way to produce a message authentication code. As you can imagine, message authentication codes ensure message integrity and message authenticity. So finally, how does a message authentication code work if it has nothing to do with encrypting data? Well, let's say we have 2 people, a sender and a receiver, who want to ensure that their messages have been transmitted without anyone changing the content of the message while it's been in transit. So how this would work is that the sender starts by writing a message, and then they simply broadcast it here out in the open. Again, message authentication codes have nothing to do with message confidentiality. At the same time, the sender also uses a MAC algorithm using a certain key that they have agreed with the recipient beforehand. So this key could be used to secure communications by encrypting, but in this case we will use it to ensure message integrity instead. The MAC algorithm produces a message authentication code which the sender attaches to the end of the message. Now both the message and the authentication code can be sent out in the open. So then the receiver receives both the message and the message authentication code. And because the receiver knows the key, they can use these two inputs, the message and the key, and use the same MAC algorithm to determine the message authentication code for this particular message. And then they simply compare the two message authentication codes, one that came with the message and one that came from their own calculation. And if these match, then the message is authentic and integrity is checked. Otherwise, the message has been tampered, or some of the communications have been corrupted. Maybe some packet loss or something has occurred during the transit of that message.